Hello once again, Theory 4 students. Today, as I am taping this, the day is Monday, April 20th, and it's a pretty nice day outside. It's getting warmer, the sun is out, and hopefully we will not have any more snow before the end of the semester. So today I'm going to talk to you today about what are called interval classes and interval vectors. This is one of the last topics that we need to discuss before we have a basic or fundamental knowledge of how to analyze atonal music. So what I'll do is I'll first of all compare or talk a little bit about the relationship between traditional intervals and the intervals that we deal with in atonal music, that is the number of semitones or half steps there are in an interval. And then after that we'll move on to interval classes and then finally interval vectors. So what I have on the board right now is a list of all the traditional intervals that we have learned ever since Theory 1 over in the left column here and over on the left side of this column. And then on the right side of each column I have the number of half steps contained within each of those traditional intervals. So here on the right side of this column and then on the right side of this column you can see the number of half steps contained within each traditional interval. I find that this can be very helpful knowledge. Not that you need to memorize this information, but it certainly can be helpful when you're trying to think in terms of translating from traditional intervals to atonal intervals, which are measured in half steps. So we can see, for instance, that the unison, the perfect unison, contains no half steps between the two pitches. The minor second, 1 half step, major second, 2 half steps, and so on and so forth. Down here on the bottom of this column I have TT, which stands for tritone. And any tritone that is an augmented fourth or a diminished fifth will contain 6 half steps. Over on the next column here you can see perfect fifth all the way down to a perfect octave, and a perfect octave contains 12 half steps. So again, you don't need to memorize this, but it might be helpful for you to put in your notes and to keep written down somewhere for you to refer to in case you need it. The next thing I'd like to do before going on to talk about interval classes is to take a pitch class set in a random order, and I would like us to go through the steps on how to find the prime form of these notes in this pitch class set. How to find the prime form. So one of the first things that we'll need to do when we're dealing with real music, the notes on a staff in real atonal music, one of the first things we need to do is we need to get rid of or eliminate any pitch class duplications. Any pitch class duplications. So for instance, if I look at the 4 notes that I have listed here in this measure, and they can be in any order, it doesn't matter, I have E, F, G, and F flat. Now if you think about that, we're dealing with atonal music and we're dealing with pitch classes. You will recall then that E and F flat both belong to the same pitch class because they are enharmonic with one another. And so what we want to do is we want to eliminate or we want to delete any pitch duplications before we start finding the normal order and eventually the prime form of our pitch class set. So what I'm going to do is I can basically scratch this pitch completely. I don't need to deal with an F flat because E enharmonic with F flat represents that same pitch class anyways. And doublings of pitch classes are meaningless in atonal music. Okay? So we only need one instance of each pitch class. And when each pitch class is represented, then we'll have our pitch class set. So it looks like my pitch class set is going to contain the pitches E, F, and G. E, F, and G. And so I can go ahead and list those. I can use letter names, first of all, E, F, G. And again, it is, at the outset, it is an unordered pitch class set. So I use curly parentheses with commas. Now, when I look at these three pitches, E, F, and G, I can see off the top of my head that the smallest distance or shortest possible distance between the outside notes when I list them in ascending order within an octave is going to be this order right here, E, F, and G. For instance, if I quickly write them up here, if I start with the E and then F and G, and I use another arrangement starting with the F, and then I go within the span of an octave, again, F, G, and E, and then there's only one more arrangement, and that is if I start with the G, I have G, E, and F. You can see that out of these three possible orders or arrangements, that this first one, E, F, G, is the smallest order between the outside notes. Right? The distance from E to G is a minor third, and we know that that contains only 3 half steps. So I can tell that this is going to be my normal order, first of all, of my unordered set. And I'll go ahead and list the normal order right away in terms of pitch integers, pitch class integers. So my normal order is going to be 4, 5, and 7. Remember, that's one of the steps to finding prime form of any pitch class set. Okay. When I reduce this normal order so that the first number is a 0, what I will do is I will subtract 4 from all of these pitch class integers, and I will get the normal order that starts with 0 of 0, 5 minus 4 is 1, and 7 minus 4 is 3. Because remember, prime forms always begin with 0. And this is going to be one of the important normal orders that I compare with another normal order in order to find out which one is smaller, which one is prime form. So let's get that other normal order. What I need to do is I need to invert this set. And a quick way to invert the set and still have a 0 within the set is to subtract all of these members from the largest one, which is 3. So let me go ahead and write that over here. And remember, when we invert a normal order, it knocks it out of normal order. But 3 minus 0 is 3. 3 minus 1 is 2. And 3 minus 3 is 0. Generally, when we invert a set this way, over 9 times out of 10, the set will come out to us in reverse normal order, the exact reverse normal order. So all I need to do is rewrite this in ascending order with the 0 first, and it will be in normal order. And that is going to be 0, 2, 3. Okay, so this is one representation of all the transpositions of a pitch class set, of a set class, I should say, starting with 0. And then this is another one that starts with 0 that represents all the inversions of a set class. When I compare the two, all I need to do is add the integers in each of the pitch class sets. And 3 plus 1 equals 4. In this case, 3 plus 2 equals 5. Whichever pitch class set or normal order here yields the smallest sum, that will be your prime form. So it looks like this is going to be my prime form, 0, 1, 3, and I can list it officially as, with curly parentheses and no commas, 0, 1, 3, that is the prime form of this atonal pitch class set, the one that contains pitch classes E, F, and G. And you can go into the appendix of in the back of your book and you can check. And 0, 1, 3 is one of the trichords, or one of the set classes in the back that contains 3 pitches. Okay, so that's just a quick or a little review about how to find the prime form of a set. You don't want to forget that, obviously, for tests that will be coming up. So let's leave it at that, and let's move on then now to talk about what an interval class is. So musicians need to know, at least musicians that analyze atonal music, they need to know what intervals are found between each of the successive pitch classes in a pitch class set. Okay? All of the intervals contained within a set are known as the interval content of a set. Now, it's kind of an important word. It's not as important as interval class or interval vector, but the interval content of a set is basically a description of what are all the intervals between all the successive pitch classes in a pitch class set. In order to determine the interval content of a set, we must first categorize intervals according to interval class. Interval class. And this is the more important term, interval class. It's not exactly like what a traditional interval is. It's similar, but it doesn't represent the same information all the time. So let's just define an interval class as the shortest distance between 2 pitch classes, irrespective of octave or direction. Let me write that down. An interval class is the shortest distance between 2 pitches, or 2 pitch classes, I should say, irrespective, that means without regard to any octaves or direction, irrespective of octave or direction. Okay, so with interval class, we are concerned primarily with, we're most interested in the shortest distance between any 2 pitch classes. And again, I'll show you an example in a second. Octave or direction, whether your interval goes up or whether it goes down, that doesn't matter. It's immaterial to interval class. So let's take a concrete example here and look at one that is, we want to find out, in other words, what the interval class is between C, the pitch class C, and the pitch class B flat. Now in terms of a traditional interval, tonal interval, we know that this is a minor seventh. And as such, the minor seventh contains 10 half steps. So, C up to B flat is 10 half steps. But the B flat that is an octave lower than this B flat, for instance, if I move it down here and I go to this B flat an octave lower is also a member of B flat's pitch class, is it not? Because remember, in a pitch class, octave does not matter. Any note, regardless of its octave or regardless of its enharmonic spelling, as long as it sounds the same, again, not with regard to the octave, that is a member of the same pitch class. So I'm saying that this B flat here also belongs to this pitch class of this B flat here. An octave doesn't matter. So, since this B flat is also a member of this B flat's pitch class, and this distance between C and B flat is shorter than the distance between this C and this B flat, then the number of half steps between these two pitches is going to represent our interval class between the notes C and B flat. Okay. Again, direction doesn't matter, octave doesn't matter. So how many semitones or half steps are there between this middle C and the B flat right below it? Well, a traditional interval, that is a whole step. And so that gives us the number of semitones in a whole step is always 2 half steps, or 2 semitones. Okay? So, because the distance between this C and this B flat is shorter than the distance between this C and this B flat, we're going to say that this distance represents what's called an interval class, not the larger distance. Okay? So because the distance between C and B flat is 2 semitones, we would say that the interval class that this C and B flat belong to, they are a whole step apart, they belong to interval class 2. Again, because there are 2 half steps between them. Interval class 2. Alright, now, any interval and its traditional inversion belong to the same interval class, right? So for instance, again, using this example, which one is going to be the shorter distance? The major second or its inversion, the minor seventh? Well, the major second is always going to be the shortest distance rather than the minor seventh. So 2 semitones or interval class 2 represents the interval class, or it is the interval class for both the minor seventh and the major second. For both the minor seventh and the major second. And when we apply this process to all of the traditional intervals and their inversions, we find out that in atonal music there are 6 main interval classes total. 6 main interval classes. Each interval class, again, represents the number of semitones in an interval or its inversion, whichever is shorter. Whichever is shorter. So, let me go to a different screen here to show you what the 6 main interval classes are. I believe I wrote them down. Yes, and here they are. Up on the top rows, I have traditional interval names. And down in the bottom row of this chart, I have the interval class. And you can see that the first one in this table is the one that I just used as an example. The minor second and the major seventh both belong to the same interval class. And that, oh, I'm sorry, I did this one. The major second and the minor seventh, that was the one I used as an example. They both belong to the same interval class, which is interval class 2. We abbreviate interval class as IC. It doesn't stand for ice cream. It stands for interval class in the atonal theory. Okay. And the reason that this interval class is interval class 2 is because there are 2 half steps in the smaller of the 2 intervals. The major second and the minor seventh. The shortest distance is the major second out of those 2, and it contains 2 half steps. So I think you're getting the idea. What we can see from this table now is that the minor second and the major seventh, they both belong to interval class 1, because the minor second is the shorter of those 2 intervals, and it only contains 1 semitone. By the same token, a minor third and a major sixth belong to the same interval class, and that interval class is 3. The major third and the minor sixth belong to interval class 4. The perfect fourth and the perfect fifth belong to interval class 5. And the augmented fourth and its inversion, the diminished fifth, they each contain the same number of half steps between them, because both of these intervals are known as the tritone. And both these intervals contain 6 half steps, so they therefore must belong to the same interval class 6. Again, one other way to maybe phrase or think about what an interval class An interval class is the measurement of the distance between two pitch classes following the shortest possible path. Inversions, octaves, direction, and order, all that stuff does not matter. Just take any two pitches and find the shortest possible distance between them, and you will get the number of semitones between those two notes will be your interval class. Interval class. By the way, this table is found in your book on the bottom of page 514, and you can refer to it there unless you've already written this in your notes. It doesn't hurt to have this in your notes either. But before I leave this table, there is technically one more interval class, and that interval class is for the intervals the perfect unison and the perfect octave. And I guess technically I can write that over here. So for instance, the perfect unison and the perfect octave, the shortest distance of these two, the unison or the octave, is going to be the unison. And of course there are no half steps in a unison. There's no space at all between two notes that are in a perfect unison. So this interval class is actually represented as IC0, or interval class 0. Now, when we deal with pitch class sets and finding the interval content of those pitch class sets, we're not going to have to deal with the perfect unison or the perfect octave or interval class 0 at all, because as we saw at the beginning of this lecture, enharmonic pitches and pitches that are an octave apart, all that, they belong to the same pitch class, so we're never going to have to use this particular column. But I point this column out to you because there may be just some general problems in the future where we have to find out what is the interval class for an octave. And that interval class will always be 0, interval class 0. Right, before I move on now to interval vectors, let's just get a little bit of practice identifying interval classes. And for that, I believe I have prepared, right here. I've prepared a screen that we can identify what interval classes do all of these traditional intervals belong to. Let's go through that. Shouldn't take very long. Looking at the first one, you see F to G. That interval traditionally is a major second. So the number of half steps in a major second is 2. So this distance will be represented by interval class 2. Right? The inversion of a major second, the minor seventh, is going to be too many semitones. And by the way, we don't have any interval classes that go beyond interval class 6. That is our largest interval class. Because any of the larger intervals, the ones that contain more than 6 semitones, their inversion is going to be the shorter distance, and so we can get a smaller number for our interval class. Alright, the next one, E up to C sharp, that is traditionally a major sixth, but we know that a major sixth inverts to a minor third, and how many half steps are in the shorter of those two, the minor third that is? Well, there should be 3 half steps in a minor third. So even this traditional interval of a major sixth, that belongs to interval class 3. And you should be able to check this with the chart that I just gave you, or on the bottom of page 514 in your text. In fact, I can put the traditional interval names up here. This is a major second. This is a major sixth. The next one happens to be a perfect octave. To what interval class does a perfect octave belong? Well, it belongs to interval class 0. Because the inversion of a perfect octave is the perfect unison, which has no half steps. The next interval traditionally looks like it's a tritone. You could call it exactly an augmented fourth, the way it's notated. We should know from our chart that I just talked about that a tritone always belongs to interval class 6. There are 6 half steps between an E flat and an A. And even the inversion A to E flat will also contain 6 half steps. So interval class 6 is what we have for any tritone. The next traditional interval here is a major 7th, C to B. But we know that the inversion of a major 7th is a minor 2nd. So the interval class, again the shortest distance, is going to be interval class 1. A couple more here. B flat to F is traditionally a perfect 5th. The inversion of a perfect 5th, which is a perfect 4th, is smaller than a perfect 5th. So we will use the number of half steps in the perfect 4th. And that will be our interval class. So the number of half steps in a perfect 4th is 5 half steps. So this perfect 5th belongs to interval class 5. And finally, G flat to B flat, that is, as written, a major 3rd. And we know the inversion of a major 3rd would be much larger, so we don't have to concern ourselves with that. How many half steps are in a major 3rd? Your answer should be 4. So therefore, a major 3rd belongs to interval class 4. Okay, so this is just the information, again, about what an interval class is, how to calculate an interval class. These are necessary things to know before we move on to what's called an interval vector, which I will start discussing now. In order to understand what an interval vector is, first of all, we need to know that when you have a set that contains 3 pitch classes, let's say the set is 0, 1, 3. Any set that contains 3 members or 3 pitch classes is going to have a total of 3 interval classes. In other words, there are only 3 total intervals between each of the successive combinations of pitch classes in this pitch class set. If you have, let's say you have a set that contains 4 members or 4 pitch classes. Any set with 4 pitch classes will always have 6 interval classes. So once again, a set with 4 pitch classes in it will always have 6 interval classes. A set with, and again, whatever the set may be, let's just use some unordered set rather than a prime form. Let's say this set is 2, 4, 7, and 10, and 11. Any pitch class set with 5 members is going to contain a grand total of 10 interval classes. There will be 10 intervals, again, between any combination or pair of integers in this pitch class set. So, 10 interval classes. And I think that's as far as we need to go. We don't need to know how many interval classes there would be you could get in a set that contains 6 members or 7, etc., etc. We're mostly going to be dealing with pitch class sets that have 3 members or 4 members. All right. Now, to determine the interval content of any set, determine the interval classes between each pair of pitches in the set. Let me say that one more time. To find the interval content of a set, we're going to determine the interval classes between each pair of pitches in the set. And by the way, once we find the interval content, then that information we will use to write what's called an interval vector. But let me not get too far ahead of myself. Let's go ahead and make another some space for another screen here where I can give you an example. We want to find the interval content of a set. That is, how many intervals and what are the interval classes between each pair of members of a set. So let's use one that I've been using for the last however many weeks. Let's use the set G, G sharp, and B. And I know that this is already in normal order. We've used that many times. And so I have it written here using square brackets because it is in normal order. Okay? So what we're supposed to do is we're supposed to find the interval classes between each pair of pitches in the set. Well, let me go ahead and write them. Let's see, do I want to write them here? No. Let's write them here. We said our set is G, G sharp, and B. Okay, so we know that since there are 3 members in this set, that there are going to be a total of 3 interval classes when we're done. So let's go ahead and find what the interval classes are. The interval class between G and G sharp, that's just 1 half step, so that's going to be interval class 1. The distance between G sharp and B, which is traditionally a minor third, that belongs to interval class 3. There's only one other interval to check, and that's the distance between the first note and the last note, G to B. Since that traditionally is a major third, G to B, we know that that contains 4 half steps, and so therefore this should belong to the distance G to B belongs to interval class 4. All right, now we have all the information we need to write down what is called an interval vector. All right. Once you know all the interval classes within a set, what we do is we list the number of occurrences of each interval class from left to right in ascending order. From left to right in ascending order. So you can kind of think of it like this. Let's go ahead and list what are all the possible interval classes that we have here. Interval class 1, 2, 3, 4, 5, and 6. Again, interval class 0 will not enter into the equation when you're finding interval classes within pitch class sets. Okay? So of these 6 possible interval classes, we're just going to list the number of instances we have of these interval classes in this table. We're going to kind of just tabulate them. So we have, it looks like we have in this set an instance of interval class 1, and we just have 1 occurrence of that interval class. So we're going to put down 1 in the interval class 1 column. Do we have any instances of interval class 2 in this set? No, we don't. We didn't find any. So there are no instances of interval class 2. We're just going to list 0 in the interval class 2 column. Interval class 3, yes, we have 1 occurrence of that. So we're going to put a 1 down here for interval class 3. Interval class 4, yes, we have an occurrence of that. We have 1 occurrence. So I'll list that as, tally that as 1. And then there are no instances at all of interval class 5 or interval class 6. So I'm going to put 0 in each of those columns. And what results now is a 6-digit number called an interval vector. Okay? What is our interval vector? Well, it is, and you don't have to put this in any kind of parentheses or any kind of border or anything like that. But our interval class for this pitch class set, or excuse me, our interval vector, let me write it in another color, is 1, 0, 1, 1, 0, 0. That again is 1 instance of interval class 1, no instances of interval class 2, 1 of interval class 3, 1 of interval class 4, and no instances of interval class 5 or 6. So an interval vector is, again, it's a 6-digit number. It's a string of 6 numbers, and they are just basically the number of occurrences of each of the 6 interval classes that we find when we go into the pitch class set and look for them. Okay. So here is my interval vector for the pitch class set G, G sharp B. It's 1, 0, 1, 1, 0, 0. Now, I'm going to go through another example here to find the interval vector of a set. And let's just say, for instance, that you don't have staff paper or music manuscript paper in front of you, and you don't have a way to list the pitches of your pitch class set on a staff so that you can calculate the distance or the interval classes between each pitch. Well, you can still find the interval vector without recourse to a staff. Let's take another pitch class set example, and let's not use a staff at all. By the way, if you do not have a staff, I'm going to use this screen. If you do not have a staff, generally the easiest way to find your interval classes and the interval vector of a set is to use the prime form of a pitch class set. To use the prime form of a pitch class set. And the reason we do that is because this set will always begin with 0, and the remaining members of the set will represent how many half steps they are above 0. So for instance, let's take the prime form 0, 3, actually let me put it down a little bit lower so I have some space to use. Let's find the interval classes and the interval vector of the prime form 0, 3, 4, 7. We know that since this prime form begins with 0, that the next pitch class integer in the set is 3 half steps above it, and this one is 4 half steps above 0, and this last member of the set is 7 half steps above 0. That's basically, these numbers are just the number of half steps above 0. So using the prime form is generally the easiest way, I feel, to find the interval vector of a set, because everything is what it looks like. It's basically just these numbers, which are the number of half steps above 0. Okay, so to find the interval vector of this prime form, what we need to do is we need to look for we need to find all the interval classes contained within the various combinations of pitches in this set. So this is the way I do it in order to not miss any combinations of pitches or miss any interval classes. What I'll do is I'll just start from the first member of the set, and I'll find the interval class between the first member and the second member. Then the interval class between the first member of the set and the third member of the set. Then the interval class between the first member of the set and the last member of the set. And then what I'll do is I'll find the interval class between the second member of the set and the third, and the second and the fourth. And then after that, finally, I'll find the interval class between the third member and the fourth member of the set. And that will get me all of the possible intervals contained within the set. Alright, so starting from the interval classes to each pitch in turn from 0. We know 0 to 3 is 3 half steps, and that's small enough to be an interval class. So this is IC3. 0 to 4 is 4 half steps, so that's going to be interval class 4. 0 to 7, however, 7 is a little too large to be an interval class. The distance from 0 to 7 or 7 half steps is technically a perfect fifth. And what interval class does a perfect fifth belong to? Well, it belongs to the interval class of its smaller inversion, the perfect fourth, which is 5 half steps. So you have to be careful. You can't just write interval class 7 for this because there's 7 half steps between them. Remember, that's too large. We only have interval classes that go up to 6. The inversion of a perfect fifth, or 7 semitones, is a perfect fourth, or 5 semitones. So technically the interval class between this member of the set and the last member of the set is interval class 5. Okay, continuing on. Now we're going to find the interval class between these two pitches of the set and then between these two pitches of the set. So 3 to 4, that's just one semitone or one half step. So that's going to be an instance of interval class 1. 3 to 7, 7 minus 3, there's 4 half steps in between there. So here's another instance of interval class 4. And finally, the one that I didn't get to yet, and, well, I guess I could put it up here even in a different color. That is the distance between pitch class 4 and pitch class 7. What interval class do those two, what interval class represents the space in between them? Well, 4 to 7, 7 minus 4 is 3, and that's small enough to be an interval class. So we're going to say interval class 3. All right. Now, you may recall a few minutes ago I mentioned that if you have a pitch class set with 4 members to it, you should get a total of 6 intervals, or 6 interval classes. Well, let's see. We got 1, 2, 3 here, 4, 5, 6. That's it. There's no more than 6 intervals between all the various pitches in any combination in this pitch class set. So we know we've got them all. Now, what I need to do is I need to list the interval vector for this set. And again, the interval vector is just a tally or a listing of how many instances or occurrences of each interval class there are. And we're always going to start with interval class 1 and go all the way to interval class 6. So if I just kind of make that a little bit over here, I'll make it really small. 2, 3, 4, 5, and 6. Okay, let's tally them up. How many instances of interval class 1 did we find? 1. So I'm going to put a 1 there. How many instances of interval class 2 did I find? None. So I'll put a 0 in there. How many instances of interval class 3? Well, it looks like I found 1 there and I found 1 here. So that's 2 instances of interval class 3. Interval class 4, I also have 2 instances, 1 here and 1 here. Interval class 5, looks like I just have the 1 instance, so I put a 1 there. In interval class 6, I did not find any instances of that interval class, so I'll put 0 there. Thus, the final answer for the interval vector is this 6-digit number. 1, 0, 2, 2, 1, 0. This is my interval vector. I've always wanted to have a student at this time in Theory 4, a student named Victor, so I could ask him, what's your vector, Victor? Okay. I hope that between the last example and this example, I hope you've seen enough to be able to calculate all of the interval classes between any pair of pitch classes in a pitch class set. And then when you calculate all those interval classes, then you tally up how many instances of each interval class there are, interval classes 1 through 6, and you just list them in order from left to right, from smallest to largest, how many instances there are of each interval class. Now, one other thing you can do, perhaps to slightly check your work to make sure your interval vector is close to being correct. Notice again, as I said, with a pitch class with 4 pitch class members to it, we're going to have 6 total intervals. Does 1 plus 2 plus 2 plus 1, does that equal 6? Yes. That means you didn't miss any intervals when you were checking them. You've got all 6. There was 1 of interval class 1, 2 of interval class 3, 2 of interval class 4, and 1 of interval class 5, and none of interval classes 2 or 6. Okay. Let me also show you another way that you can check your answer for your interval vector in the event only when you have the prime form of a set. So I have gone into Appendix C in the back of your book, and because the example I just did was a four-member set, I'm going to look at the column that contains all the prime forms for four-member pitch class sets. This happens to be on page 560 in your textbook, and because I know the prime form, because that's what I started with, that's what I was using to find the interval vector from, my prime form that I started with is 0, 3, 4, 7. Well, in the appendix there is also a column that lists the correct interval vector for all of the prime forms in atonal music. That's pretty nifty. I think it's pretty handy. So we can look in this same row now with 0, 3, 4, 7. We can find that the interval vector should be 1, 0, 2, 2, 1, 0. I believe that is exactly what we found just a minute ago for our set 0, 3, 4, 7. Again, if you know the prime form, or if you are working from a prime form of a set, that is the set class's name, that's what a prime form is. If you know that information, you should be able to go to the appendix in the back of your book and check the interval vector to see if you got it correctly. If you do not have the prime form of a set, then you can't necessarily come back here easily and check your interval vector. You'll just have to trust and check your work that the interval vector you calculated is right. Again, when you do not have the prime form. But any prime form, any set class, which is listed in the back of your book in the appendix, should list the correct interval vector. So again, an interval vector is a 6-digit number that lists the number of occurrences or instances of each interval class between any pitches within a set, within a pitch class set. Okay. You've got to remember to check every single interval between every combination of pitches in your pitch class set, and turn those interval, those number of half steps into interval classes, and then just list the number of interval classes, and you'll have in an order, and you'll have your interval vector. At any rate, the last thing I want to basically say to you or tell you about this index is that there are some set classes in atonal music that, even though the set class is different, for instance, there's one here called 0146, and there's one at the bottom here called 0137. And even though the set class is completely different, these two set classes turn out to have the same interval vector. And that's kind of cool, at least to me. That means they have the same internal intervals, the same number of instances of the same interval classes between or among their pitches. Okay. And any set in the appendix that is listed, the Fort name column over on the far left, if any Fort name set class is named with, or contains a Z in the name, that means we say that that set is Z-related with another set class. And Z-related means the two set classes have the same interval vector. Their interval vectors are identical. So if we look, for instance, at this one, 4z15, which is the prime form 0146, we see that its interval vector is actually one instance of every interval class. 1, 1, 1, 1, 1, 1. Now, how do I find the other, I should say, set class that contains the exact, or that has the exact same interval vector? Well, just go down the list into the Fort name category and find another one with a z in it. And we have to go to the very bottom here, 4z29. The set class or prime form is 0137, but its interval vector is also identical to this interval vector here, which is 1, 1, 1, 1, 1, 1. Again, so as you're paging through your appendix and you're looking at it and you're observing it, anytime you see a Fort name for a set class, that's in the FN column, that contains a z, all you have to do is look further down or elsewhere in the column for another z and see if you can find the interval vector that should be identical with the one that has the z. For instance, if I were to go to the pentachords, which is on page 561 of your book, let me shrink it just a little bit here. And if I freeze this, I can see that there are several Fort names in the pentachord column for set classes that contain z in their name, like 5z17, 5z18, and then there's 5z36, 37, 38, etc., etc. Well, all you got to do then is, for instance, if you look at 5z18, 21, 2, 2, 2, 1, find another one that has a z in its name with the same interval vector. Here we go, 5z38 has the interval vector 2, 1, 2, 2, 2, 1, the same thing. So. Alright, so that I can wrap things up here before I hit the 60-minute mark. In fact, I don't know how long I'm in, but I bet you I'm getting pretty close. The homework for this week, which I will put on Canvas in great detail for you, is to complete all of workbook page 299. That again is finding interval classes and interval vectors. And then I want you to complete a workbook page 301, but numbers 1 through 4 only on page 301. And in the instructions to workbook page 301, it'll say that you need to include the Fort name. You can scratch that part out of the instructions. I don't need you to learn or memorize or write down Fort names at all for this class. I mean, if you want to, you can always go to your appendix and write the Fort name down, but you do not have to. So on page 301 in the workbook, doing numbers 1 through 4 only, I want you to start from scratch. That means you're going to be given a pitch class set that may look like this. You're going to eradicate or ignore any pitch class duplications. You are going to find then the prime form of that pitch class set. And then from the prime form, I want you to calculate interval classes so that you can come up with the final interval vector. So page 299 in the workbook, all, and page 301 in the workbook, numbers 1 through 4. Again, this is not the easiest material to teach, especially over video, but it's not impossible either. And I think if you're good with numbers, or at least know a little bit of math, it should not be too hard. But please do let me know if you have any questions. Email me or call me, and yeah, let's just. I'm sure you'll be able to do fine on this homework assignment. So let's stop there, and maybe until next week when I get you another lecture. Hope you have a good week.